Good morning. My name is Motohide Tamura from the University of Tokyo. Actually, I have just moved from the NOAJ, which I stayed for 20 years, and just moved to, but still working for both institute. And this talk is on behalf of the entire SEAS team. And yes, this team is pretty large, but it's composed about 120 members. And in fact, about 1/3 foreign peoples. So I would say this is a very international project now. And so here's my talk outline. I'm starting with explanation of what is SEAS, and then I'll explain the target of our survey and final aim of this surveys. And there are many SEAS-related posters and talks which I couldn't count well before this talk, but you can easily check on the posters. And then I will summarize some of the results. Although this session is mostly concentrating on planet and companions, so these results covering not only planet, but also disk result. So I'd like to start with a disk result, and then explain some of the planet and companion results. And then make a brief summary for the SEAS project. And at the end of this talk, I also would like to brief explanation of the Subaru's next instrument for exoplanet studies, and that is IRD and CALIS. So SEAS is an acronym for the strategic explorations of exoplanets and disks with the Subaru telescope. This is the first Subaru strategic program, so-called SSP. And this is a new open use category for the Subaru telescope. We now have 3 SSPs by now. And SEAS is the first one. And we have been allocated 120 Subaru nights in 5 years, which was started in 2009. By now, I would say about 4/5 have been completed, and I present mostly 2.5 years, maybe about 3 years result, first 3 years result in this talk. And the main aim of this program is a direct imaging and making a census of giant planets in the outer regions, around in total about 500 solar type stars, and also the massive stars. The radial regions which we are interested is a few AU to 50 AU, which has already been discussed by previous 2 speakers. The aim is more or less similar. And in addition to that, we are also exploring the protoplanetary disk and debris disk for the origin of diversity and the evolution of exoplanets, which you are already familiar at the same radial regions where we are detecting such kind of outer planets. By doing so, I believe we can make a direct linking between planets, outer planets, and protoplanetary disks. That's our goal of these surveys. For this, to achieve these 2 goals, we are now using the polarimetry mode combined with the ADI mode, so that we can also detect the reflection component of this kind of disk. And this cartoon is showing how observation techniques have been proceeded in the previous instrument, so-called CHAO. This is a coronagraph with low-order adaptive optics. And this is our instrument, which we are using right now. With the previous instrument, we can detect the planet at, say, 100 AU, like the GQ loop or DH tau. But also, we can study the disks, but the radial distance is more than 100 AU. But with this new instrument, you can detect the planet at, say, 30 AU or even less. And also, you can study the disk structures starting at about 5 AU to, say, less than 50 AU. So the resolution is improved about 2 or better. And also, the contrast is much more improved by 10 compared with the previous instrument. this is a more graphical showing how we can revealing the outer, so-called outer planet. As you are already familiar with, previous radial velocity and the transit method have detected the hot Jupiters and hot Neptunes and super Earths in these days. And those are very close to the central stars. And our solar system is situated like this one, but direct imaging are actually detecting very massive, which I mean several Jupiter mass objects situated beyond the Jupiter orbit. So that's very difficult to explain with the standard quark collision models. So, but those we have witnessed that this kind of object really existed. But we don't know how they are formed with a standard quark collision model or other kind of models like the gravitational instabilities. So we do need to explore the origin of such kind of outer planets. Okay. So the key instrument for this survey is a HICHAO. This is a high contrast instrument for the next generation adaptive optics developed for the Subaru telescope. And myself was a PI and collaborating with Klaus Hodap at UH and Ryuji Suzuki, now at the TMT project at the NOAJ. And the instrument was completed 2009. So as soon as this instrument is completed, we have started these surveys. And the big important thing is this instrument has no major trouble from that time. So that is very critical for the, such kind of large survey so far. And the instrument is combined with curvature sensing adaptive optics with 188 elements right now. And it is also becoming combined with so-called extreme AO, so-called SKEX AO, developed by Olivier Guillon and Franz Martinez. And I don't go into the details of this instrument, but this instrument is using the latest architecture at that time, such as a 2K detector with the ASIC readout. And we are constantly improving the performance of this instrument. Okay, so this is our target. We have the so-called several categories. And categories are YSOs, moving cluster MG, open cluster OC, nearby stars NS, and debris disk DD. And those are spanning this kind of age, starting around 1 mega year through around 1 giga years. The reason for this kind of large span of the age is, as you are already familiar with, if you plot the evolution of such various kind of objects, including planet mass object, brown dwarf, stars, whatever they are very bright at the, when they are young. This is a log age and log luminosities, and the theoretical calculation for the, based on the so-called hot start model already introduced by Bess. And so the YSO category is spanning this range, so from 1 mega year to 10 mega years. Our target is mostly from Taurus and also several targets for the southern hemispheres. Although the elevation is not good enough for the Hawaii, but we are trying some too. And for the moving group and DDE, their age is roughly covering from 10 mega year to 100 mega years. For the open clusters categories, we are now concentrating the Pleiades. So the age is around 120 mega year or so. And for the nearby stars, we are selecting very nearby stars based on various methods. And the age spans which we have selected is ranging from 100 mega year to about 1 giga years. So by combining all these targets, we can span the target whose age range from 1 mega year to about 1 giga years. Another reason why we are trying to cover various age range is the problem of the planet formation theories. I'm not sure it's a problem or not, but we have the so-called hot start model, cold start model, and even in these days, we have the warm start models. So we don't know which one is the right one to explain the evolution, luminosity evolution for the planetary mass object orbiting around the stars. But if you plot this cold start models, their expected luminosity is much less than the hot start models. But this situation is mitigated when they are aged in, for example, several 100 mega-year old. Their difference is much smaller. So if you find any planet around such kind of relatively older stars, our mass estimate based on the luminosity is more reliable than for the young, those for the young stars. So that's another reason why we are spanning various ages. But as you know, the younger stars are more easily detected. So we have the kind of problem when they are young, they are brighter, but their mass estimate is not always reliable. But when they are older, their mass estimate is more robust, but it's difficult to detect. Okay, so here's some papers so far published for each categories base. For example, we have about more than 20 papers, published papers so far from this project. And there are many YSO papers based on each result of the YSO target. These are mostly these papers. But we hope to find any young planet, very young planet in this category too. But others are some statistical papers like the moving group, OC group, and DD group. And also some individual target paper for the nearby stars. So I'd like to explain some of these results very quickly. Okay, this is one of the highlights of the disk result, our disk result. This is a gallery, kind of galleries of the sheath disk data with a resolution of 0.1 second. So it's a typical distance of 100 parsec, and this spatial resolution of this image is less than 10 AU. So you can now see the disk structures less than 10 AU scale, very close to the central stars. And not only this kind of very simple disk structures, what we are seeing in this image is a detection of morphological diversity of protoplanetary disk, like the gaps, this ones. Yeah, you can clearly see such kind of large gaps, and ring structures, and some spirals, very small scale spirals, less than 100 AU spirals for at least 2 sources, and also some bridges here. So we are very interested in this kind of structures, how these are made from. And for example, this is large gaps detected by one of the solar mass stars, 0.8 solar mass stars, very young. And you can clearly see the large gaps with a very sharp edge, inner and outer edge. So I think this is caused by laser photoevaporation, but the most likely cause of this large gap with a very sharp edge is a multiple planet origin is most likely, because this kind of simulation suggests can produce such kind of large gaps in the protoplanetary disks. And this is an imaging result of the debris disk HIP 79977. And this is the first imaging detection of a disk of this particular target. And the disk is extended up to 300 AU. But the interesting point of this data is if you remove this small component, you can see some hint of the point-like source situated here. If this is a planet, it's only a 4-Jupiter planet, or it could be just a clump of dust situated around 60 AU. And it's already published by Christian Thalmann last year. And we have new planet candidates. One is already published, Kappa Andromeda. And this is a massive planet around one of the most massive stars. And this is just published by Joe Carson. And this is actually, this is a proper motion, of course, proper motion confirmed object, and its color is very red. So it's very similar to other directly imaged planet. And another one, which I cannot show you the name today, unfortunately, because it is still under referring. This is the least massive planet, we believe, and ever imaged for the sun-like stars. So it's, if our age estimate is correct, it is only 3 or 4 Jupiter mass situated at 40 AU. And as I mentioned, since this star is relatively older than other objects which have been reported for the direct imaging, I think the model dependence is more small. So the our mass estimate is very reliable, whatever model you used for the luminosity evolutions. So I would say this is a very strong constraint for the planetary formation theories for the outer planet around G stars, not only A stars. And we also have more candidates which should be confirmed by spectroscopy too. Okay. And I should skip some of these results, but yes, this paper is already published. So this is about 13 Jupiter mass object orbiting around 50 AU. And this is a very robust detection, I would say. And another point which I would like to briefly mention is detection of the radial velocity target is also very important in this direct imaging, because we have recently detected companions. This is not a planet. This is a relatively massive companion. But the detection of this companion with a common proper motion is very important to interpret the origin of the retrograde motion of this first detected retrograde planet, HAT P7b, because this planet is origin of the retrograde motion of the inner planet. And that one is just published for Narita-san. And this is the sum of the statistical result for the Pleiades. And we have the, with these papers, we have only used 20 stars, but we can put some constraint of the upper limit of the frequency of the outer planet, less than 18% or something like that. And that is just accepted for the Japanese journals by Yamamoto-san and Konishi-san. So CIS is directly detecting outer planet and the candidate, 2+1 planet so far, and a few brown dwarfs and other candidate. And CIS also detecting the signpost of planet via directly imaging the unprecedented details of the protoplanetary disk and some of the debris disk. So we are now still individual studies of these interesting results, but statistics are coming in very near futures. So I just put some very comment on the new instrument which we are developing for the Subaru telescope. One is we are building the infrared spectrometer for Earth-like planet around, to detect Earth-like planet around the M stars. One is IRDs. So I expect the first flight of this instrument is sometimes next year. And another one is the Caris. And this is very similar to other spheres and GPI, but our instrument is in the northern hemispheres. So I think this would be complementary. And this instrument is built at Princeton University. So I think that's it for my talks. Thank you for your attention.
I appreciate that you can't say too much about it, but the SEEDS P detection, so it's a few Jupiter masses at 40 AU.
Mm-hmm. Yeah.
So I wonder if you want to comment on the statistics that it sort of starts to talk about when you compare that to the previous presentation where there's no detections in that zone in the around star-like
right.
planets.
And yes, and this is if you just concentrate on the G stars, there's only one, I think, reported by from the David Lafreniere, but that's for the very young stars. But in our case, it's about 200 mega year old or something like that. So it's a very unique target, I think. So for the statistics, I would say it's very rare at present with the current surveys.
One last question.
In addition to the Happy 7b, did you check on the companions around all other systems with hot Jupiters?
I'm sorry.
In addition to the Happy 7, did you check whether there are companions around all the other hot Jupiter host stars?
Yes, we also did radial velocity surveys, and we also detected the so-called C component between the B and our direct imaged companion. So based on that data, we didn't find any additional hot Jupiters. Yeah.
Okay, let's thank the
Thank you.
again.
Thank you.